Earth, the cosmos, everything we can observe with instruments we've created, everything we know is made up of normal matter. But all that doesn't add up to a whole lot. It's just 15% of the mass of the universe. The rest is an unknown, invisible something.
If you hold up your hand, what do you see? The curved lines that make up your fingerprints? Maybe you see a scar or two. At this very second, flowing through the rings on your fingers and the hair on your knuckles are millions of particles you can't see or feel.
This mysterious substance lives under the alias of dark matter. It's one of the most staggering scientific puzzles in the history of human knowledge, a mystery that goes back to the very birth of our universe.
Luckily, our detective producers Simon Edelman and Shannon Brescher-Shea are on the case. I'm Allison Lantero.
And I'm Matt Dozier.
And with that in mind, Direct Current and Energy.gov podcast proudly presents
A Shot in the Dark, the case of the missing matter.
We're going to have a podcast about energy.
The jewels that these national labs are.
In terms of science and scientific capabilities.
Big dreams can happen.
Keeping our nation safe.
Clean energy is way of the future.
America's economic engine.
It's science
for the people.
This is Direct Current.
Of all the laboratories in all the world, dark matter had to walk into, well, none of them. Not that we could tell anyway, and that was the problem.
Hello, this is Edelman.
Hey Simon, it's Shannon. I've got a podcast idea for you.
Shannon Brescher-Shea, a scribe who's been around the science block for some time. Last time I checked, she found a niche in the Department of Energy. The Office of Science, if I'm not mistaken.
Simon, I can hear you.
Oh, sorry. What you got?
I think we should do an episode on dark matter.
Dark matter? They've been looking for that for years, and no one's ever found it. You're wasting your time, and now you're wasting mine.
See, that's where you're wrong. There have been plenty of advances, in fact. There's scientists who are doing so much right now, and...
This dame would stop at nothing to find the missing substance. I knew I'd have to take the case eventually, so I said yes.
First, never call me or any other woman a dame again, unless she actually is one with a capital D. And second, I think this is an interesting topic that not a lot of people know about. We've got experts we can talk to.
Expert, you say? Expert witness? Wonderful. Who do we talk to first?
I know just the person. Richard Gateskill is a scientist who works on the Large Underground Xenon, or LUX, and Lux Zeppelin, or LZ, experiments, two major Energy Department-supported projects searching for dark matter. He knows as much about this stuff as anyone.
Richard, this is my partner, Agent Shea.
Dr. Gateskill, I'm not actually an agent.
Let's get down to business. How long have you been investigating the dark matter case?
I've actually spent the last 28 years in the field of direct detection of dark matter. I'm at Brown University.
Can you tell us what you know about the Energy Department's involvement with dark matter?
It is very fundamental to the Department of Energy mission for basic science, for trying to understand what is the basic building blocks of our universe. You know, what is the particle model that explains not just why you and I are made of things like quarks, nucleons, and electrons, but also to understand what the majority of the universe is made of, which is composed of this dark matter. And to be able to directly detect this dark matter that's flowing through the universe and its presence in our galaxy is I think, a very important step to understanding in greater detail how our universe is put together.
Thank you, Dr. Gateskill. We'll be in touch if we have further questions.
Please just call my cell anytime, day or night.
Trust us, we will. As I suspected, this case was already starting to feel like finding the exact position and speed of an electron at the same time. Impossible.
Are you gonna keep doing that?
Maybe. Yes. Anyway, All that's well and good, but how do we even know dark matter exists if no one's ever seen it?
I'm glad you asked. Astronomer Fritz Zwicky was asking himself that very question way back in 1933. He observed the Coma cluster of galaxies through his telescope and noticed something funny. The clusters didn't move the way they should, considering the mass of stars in them. It seems like there was a great deal of matter just missing.
Let me see that file. Who's this Vera Rubin person? She was a detective as well?
No. She was an astronomer. But back in the 70s, she provided further evidence for dark matter. She calculated that if galaxies only had the mass we can observe, there wouldn't be enough gravity to hold them together. Based on how fast they rotate, they should fly apart. But Zwicky's dark matter could provide that extra gravitational force to keep the galaxies intact.
If detectives like Zwicky and Rubin can't crack this case, what makes you think we can?
Listen up. If you want to be my partner, whether we're investigating science or crime, you better keep those brown eyes of yours open. Scientists are finding new evidence of dark matter every day. The Dark Energy Survey, which uses a massive telescope to map the sky, just confirmed that dark matter actually makes up 85% of the mass of the universe. Don't ignore that.
So there's an answer out there. We just got to know where to look. All right, let's review the evidence again. What do we know? And what do we not know?
We actually know a lot about what dark matter isn't. For one, we know it's not dark cosmic clouds or other objects that don't give off light. Those clouds, planets, asteroids, and other objects are normal matter made up of our familiar protons and neutrons. But they simply don't have enough mass to make up the huge amount of dark matter needed. It's also probably not black holes. Black holes exert so much gravity that they swallow everything, including light. If dark matter does interact with light, and that's a big if, it interacts weakly, at best.
You mean like a ghost?
Not at all like a ghost. Moving on.
And we ruled out dark energy as a suspect, right?
Right.
Because that's a completely different unsolved mystery. The scientists think dark energy is causing the universe to expand more rapidly over time, and dark matter, through gravity, exerts a force in the opposite direction, trying to pull the universe together.
Exactly.
Shay, I think we're onto something here. But if we can't see it or feel it, we're going to need to think about it differently.
That's actually not a bad idea. You know who might be able to help? Philip Schuster at the Department of Energy's SLAC National Accelerator Laboratory in California.
I kind of think of it as like fog, So out in the Bay Area, of course, there's plenty of imagery for this. On a foggy morning when everything is just white, that's just moisture that's become visible, and yet now you can see it. Of course, as soon as it heats up, the moisture disappears, at least in the visible spectrum, and you can't see it. So there's all sorts of familiar things in nature that we know about, where sometimes you see it, sometimes you don't. It just depends on the conditions and how you're looking at it.
Okay, so the fog of dark matter forms halos around galaxies, including our own Milky Way.
But that still doesn't answer what dark matter is made of. We're no closer to solving this case.
Look, there are a couple of major theories scientists are looking at: WIMPs and axions. Neither of them would have an electrical charge, similar to the neutrons in many types of normal matter atoms.
Okay, I'll bite. What's a WIMP? And don't you say me.
WIMP stands for weakly interacting massive particles. If they exist, our missing WIMPs could range from the mass of a light atom, like hydrogen, to 10 times more than a heavy atom, like gold.
If they're so massive, wouldn't they stick out like a wind turbine on a mountaintop?
Their size isn't the issue. It's the fact that they interact very little. Besides, the other suspect for dark matter is even smaller. If axions exist, they'd be 1,000 billion times lighter than the lightest WIMP.
Huh. So you're telling me that even though these potential particles have such a huge difference in mass, they're both possible suspects?
Yep. Both WIMPs and axions are good candidates for dark matter because they fill different gaps scientists see in the laws of physics.
Whoa. The pieces of this puzzle are starting to fall into place.
You're starting to get it. Because dark matter is so incredibly difficult to detect, the Energy Department supports a variety of experiments that look for it in different ways. Clues have led them all the way from the outer reaches of space to deep underground, each effort with its own strengths and weaknesses.
Oh, I see what you did there.
Did where?
Weaknesses, like weakly interacting mass. And never mind. couldn't shake the nagging feeling that we were missing something. But what? I went outside to clear my head, and that's when it hit me, like a meteor falling from the sky.
And we do now have confirmation of the completed capture of the alpha magnetic spectrometer. It's made its way to its final home on the International Space Station. The confirmation coming at 4:46 a.m. Central Time.
Okay, so why are we here? What's this hunch of yours?
Dark matter may not interact with the ordinary matter, right? But what would happen if these wimps bumped into each other?
Good question. I'm assuming you know the answer?
No, but NASA might. I was listening to the archival recordings and found out they have this powerful instrument, the alpha magnetic spectrometer, that's looking for evidence of dark matter collisions. They brought it up there on the final space shuttle mission.
Wait, what happened to your accent?
Never mind that.
Anyway, what's their theory?
That they'll annihilate each other.
Jeez!
When dark matter particles collide, they should create antimatter particles. Scientists designed the AMS to detect these particles.
Scientists from where?
All over. The Department of Energy was one of the main sponsors, but there's also collaborators from MIT, the University of Maryland, Yale, and other countries like Italy, China, and France. But the AMS isn't the only effort up in space.
There's more? How much stuff did we put up there?
Well, there's also the Fermi Gamma Ray Space Telescope. That's a spacecraft that's orbiting above the Earth's atmosphere. Using that powerful telescope, SLAC scientists and others survey the universe for signals coming from areas known to be rich in dark matter.
Let's get your head out of the cosmos and get you back down to Earth.
Something big was coming. I could feel it. We seemed to be on a collision course with the answers. Like two neutrons racing towards each other around a particle accelerator at the speed of light. Hey, Shay.
Hey, Edelman.
Let me ask you something. What about the LHC?
The Large Hadron Collider in Europe?
Yeah.
Well, researchers there attempt to detect dark matter by crashing particles together to create it. They use high-powered magnets to steer particles around massive racetrack-shaped tunnels until they collide in the heart of huge detectors. While the accelerator's equipment can't detect dark matter particles themselves, they could potentially see missing energy from its creation.
Oh, that reminds me. You remember Philip Schuster?
The San Fran fog guy?
That's the one. He mentioned something about doing that kind of research at the Energy Department's Jefferson Lab in Newport News, Virginia. Let me find the tape.
And so what Jefferson Lab is able to accomplish using their electron beam and the experimental facilities they have is a very thorough, powerful, systematic search for particles that mediate interactions between dark matter and us.
Of course! The detectors Jefferson Lab uses for its A' and heavy photon search experiments are massive. They're 3 million pounds each, about the same weight as 3 747s. They've partnered with SLAC Lab to use these powerful tools to search for clues about how dark matter behaves around regular matter.
And that's really, really important because, yes, we can look for the dark matter itself. That's an important part of the whole problem of understanding dark matter. But there's only so much you learn from seeing a dark matter particle scatter off of, some object. What you want to be able to do is understand its interactions, if it's going to interact with us at all. And that's where these electron beams come in.
Oh my God, that's brilliant. Look for who or what dark matter has been interacting with, and that'll lead us to our missing particles.
Exactly. We've got another witness, Natalia Toro from SLAC. She may have some more ideas on how we could use family ties to track down dark matter.
One of the really exciting things about this possibility is that dark matter is a sort of cousin of standard model particles with its own type of, walks and talks like ordinary particles, but through its own interactions.
I feel like there might be some relation to one another.
Yeah, Schuster and Toro are married, a husband and wife team.
I was referring to dark matter and matter particles being cousins.
I got a lead in Seattle. We should check it out. It's in the basement of the University of Washington's Center for Experimental Nuclear Physics and Astrophysics. Let's go.
We turned down a dark hallway and paused at the stairs leading to the basement. Something in my gut told me this could be a setup.
It's not like that. It's just a normal lab where they keep the Axion dark matter experiment, or ADMX2.
We'll see about that.
While other experiments have looked for the results of dark matter, or the particles that go between dark and normal matter, this one looks for the dark matter itself. The experiment looks for axions by producing a very strong magnetic field. It's a promising lead.
All right. Who's in charge here? State your name for the record.
Are we recording now? Yes. Okay, so I'm Andrew Sonnenschein. I'm a scientist at Fermilab. I've been there for about 10 years now, and I have worked almost exclusively on dark matter since I got my PhD in the late 90s.
And what's your position there?
I'm the project manager of ADMX.
Tell us about the axions you've been looking for.
The axions that we look for would convert into photons with energies like microwaves. And much like the microwaves used in communications. In fact, we're looking in some bands that overlap with the bands that are used for communication signals.
Like an old-timey radio dial?
Sometimes the axion experiments are compared to trying to tune into a radio station which is at an unknown frequency. So we have the world's most sensitive radio receiver made with very fancy superconducting electronics, and we're slowly turning the dial, listening for a station. And we basically make one turn of the dial every year, despite having these incredibly sensitive amplifiers.
Hey, Edelman, if you're freaked out by the basement, you're gonna hate this next part.
Where are we? And why is this elevator ride taking so long?
This is the Sanford Underground Research Facility. Where miners once delved deep to look for gold and nickel, scientists now hunt for something even more elusive, something that can't be seen.
At the bottom of this giant, ancient elevator shaft, buried underground, one of the most sensitive detectors for WIMPs in the world lay before me. The subterranean labyrinth of abandoned mine tunnels shields the equipment from cosmic radiation and other radioactive noise under 5,000 feet of pure bedrock.
The experiments done here to find WIMPs are distinctively different from the above-ground methods. The indirect detection methods are like seeing someone's shadow instead of their actual body. In contrast, direct detection experiments, like this, hope to catch dark matter particles in the act. Directly detecting them requires a WIMP to bump into the nucleus of an atom of ordinary matter.
Shay, this place gives me the jitterbugs. Let's get out of here and talk to our next witness.
Probably a good idea. That would be Carter Hall from the University of Maryland. He worked as a scientist over at the Large Underground Xenon, or LUX experiment, the one that ended last spring.
Oh yeah, they got that follow-up experiment. What do they call it? LZ. Shay, let's play good cop, bad cop with this Hall character. I get to be the bad cop this time.
Edelman, you're always the bad cop.
Hey, be nice. Hall, tell us everything, and I mean everything you know.
You take any kind of ordinary matter made of protons, neutrons, and electrons, made of atoms, we would expect that these WIMP particles, if they exist and if they make up the dark matter, should be able to bounce off of these nuclei.
Like billiard balls, if you're playing pool.
There's an incoming dark matter particle. It's coming in from the Milky Way, basically. And very, very occasionally, it should bounce off of the nuclei of an atom. So we build experiments whose job is to try to observe sort of spontaneous jiggling of these atomic nuclei.
That sounds simple. Almost too simple, if you ask me. Shay, I gotta tell you, I'm not happy about this. There's a bad taste in my mouth. Like that time I drank liquid natural gas on a dare.
It actually sounds like simple is a good thing in this case. Looking at my notes, I see that the Energy Department actually supports multiple experiments using this technique. In addition to LUX and LZ, it's supporting a similar experiment called the Cryogenic Dark Matter Search, or CDMS, and its follow-up, Super CDMS.
All right, Shay. Hall, you're a lucky man. Dan Bauer, the spokesperson for CDMS, working with Fermilab, just put out a statement.
What Super CDMS does is to use semiconductor detectors that are cooled to very low temperature. And we try to detect the dark matter particle in two ways. One, it will liberate a tiny amount of heat in this very cold detector that we can sense, and it will also liberate a tiny amount of charge. And by comparing the two of those, we can distinguish a dark matter particle from a normal matter particle, the stuff that we're made of.
The idea may be simple, but building it certainly isn't. Some of the direct detection experiments like LUX require literally tons of liquid xenon. Imagine the headache of getting it underground.
After exploring all the possibilities and interviewing a wide variety of witnesses, not a single Dawn experiment has found a definitive dark matter signal. It was starting to feel like we'd never find the missing matter.
It's like you're a detective.
Finally, someone who speaks my language.
Yeah, I thought you'd like that. This is Hooper, theoretical physicist Dan Hooper, near the Windy City, over at Fermilab.
There's definitely been a murder.
Whoa. Murder? I thought this was a missing matter case.
It's just a metaphor.
There's definitely a murderer, all right? But you don't know. You have some suspects, and you haven't figured out which one. And it's possible none of your suspects is the guilty party. It's possible that somebody not on your suspect list did it. So, but we are trying to narrow the list, and we're trying to stay as open-minded as we can, and trying to figure out who we can rule out, who is the best alibi, so we can focus on the most likely suspects.
So now this missing matter is a murderer? Let me tell you, Shay, this case feels a bit above my pay grade.
Maybe this analogy from Carter Hall will work better for you.
You can imagine kind of a, maybe like a game show where there's a whole bunch of safes, and the job is to get in the safes and see what's inside, or see if anything is inside. The LUX experiment was designed to go after and open up a certain set of these safes. And it's not able to open up them all or look inside them all, but its job was to go after a certain set of these safes and try to do the kind of the safe cracking and break in and open the door and see what's inside.
Are you kidding? That's breaking and entering.
The LUX experiment was designed to go after the safes that we considered to be very, very compelling as perhaps being the answer to what dark matter is made of. So we carried out the experiment, we cracked those safes open, and we were able to look in places that nobody had been able to look before. And the result is that we did not find dark matter there. The basic question of what the dark matter is still outstanding. That means we have to go and look in some different places, of course. And that's what we're doing with the LZ experiment.
Safe cracking! I didn't sign up for any of this. We're in over our heads.
Calm down. You want to be a detective? Act like one. His point is that this mystery is going to require a lot more digging to solve. These big questions need big experiments and big ideas to provide big answers. Looking forward, scientists are trying new methods to look for the ever-elusive dark matter. Projects like the A' experiment and heavy photon search are just getting started. LZ and Super CDMS are even bigger than their predecessors, giving them even more sensitivity to look for a wide range of interactions.
It feels like we're back at square one.
We are not giving up yet, and neither will scientists like Natalia Toro.
Dark matter is one of these things that we know very little about it right now. All we know is that it's ubiquitous and that it doesn't interact the way that familiar matter does. That makes it very hard to search for. It means that we really have to be open to a lot of possibilities, and we have to be creative in thinking about how to test those possibilities. And that means probably we're going to have to not find dark matter again and again, several times over, before we finally find a dark matter. And it's all part of the process of figuring out what the universe is mostly made of. Because we know it's not made of the familiar stuff, we just have to keep taking, educated guesses after educated guesses, but they are almost shots in the dark. I think it's a really important problem to solve.
Another case still unsolved. If I had a nickel for every physicist that walked through that door and described dark matter like a paw print of an unseen animal, I'd...
Edelman.
While our detective producers are still on the case, you can pull this story and other stories from the digital archives at Energy.gov/podcast. Enjoy some of the links while you're there. Some of those links will lead you down a rabbit hole of videos on dark matter experiments and a whole lot more.
If you'd like to inquire more about this case or any other case you've heard, email directcurrent@hq.doe.gov or have your carrier pigeon tweet at Energy. If you enjoyed this detective tale or other Direct Current episodes, set up a community listen party. If you hear something, say something on your favorite social channel.
A decoration of excellence goes to our lead investigator and senior writer in the Office of Science, Shannon Brescher-Shea. Thank you to all our witnesses, Richard Gateskill, Philip Schuster, Natalia Toro, Andrew Sonnenschein, Carter Hall, Dan Bauer, and Dan Hooper. Nice work by our operatives in the Office of Science, Kathy Turner and Anwar Bhatti, Andre Salas at Fermilab, Michael Barnett at Berkeley Lab, and Chrissy Haynes. Thanks for being lookouts, and thank you to NASA for their cooperation in looking into dark matter.
This investigation would not be possible without the support of Kayla Hensley, Bob House, and the Energy Public Affairs Division. Direct Current is produced by Simon Edelman, Matt Dozier, and me, Allison Lantero. Courtroom sketches by Court Creer, with support from Paul Lester, Ernie Ambrose, and Atik Warich.
Direct Current is a production of the U.S. Department of Energy and published from Washington, D.C., the capital of the good old U.S. of A.
Until next time, keep your ears open and keep searching.